there are a couple things. Okay, I want to mention to the class. It's still about the project number one. I know it's probably for whoever, if you are attending the class, right, you probably know what to do. Okay, I'm recording this video right now. So for those who, I also noticed that our attendance is we only reach probably like a 50-60% of attendance. So there was an issue is about the how to say this, about how to handle project one. Okay, so there are up to now, even over the weekend, I still receive emails about how to log into Civil. Okay, so this is an issue because I have stressed the importance of getting logged into Civil almost like every class. Okay, in every class, but still there are students who didn't even try and they ask about logging over the weekend. That is to me is kind of unacceptable. Because this is not just mentioned once. I mentioned it like many times in the class. So I'm sure for those of you who are attending the class right now, you probably you probably have made that. I'm saying this is for the issue for those who are not attending the class regularly, kind of like so if you know your classmates who didn't come to class or who didn't attend the class, then ask them to remind your friends. Okay, ask them to at least to review the lecture notes. I'm also having the class going to be recorded, so they need to view the watch the video because there are problems which has been mentioned a couple of times. Is not a new problem. They're still, are asking. That's very inefficient. Okay, and it's kind of like a become a problem. So this is the first thing I want to. This is the first thing I want to stress is about the like things we mentioned in the class. I expect if I mention something in the class, okay, I expect that the information should be passed. Then it's your choice, okay? It's your choice. If you actually it's actually not your choice, okay? You are required to attend the class. But if you miss the class, okay, make sure you review the notes, review the watch the video, and make sure the information you got the information. Okay, I'm also gonna post this is on the I'm also gonna post this is to the class website. Now I even realize even for the information I post on the class website, people still don't read it, which is that's even become an even bigger problem because anything if I make an announcement in the in the classroom, that's important. Okay. Or the example I will give to you is again, there's nothing against everybody or is not to this information mostly is not to the one you are in the class right now. Okay, it's more to the students who are not here. Because like I said, for project number one, you can submit multiple Slurm files. Okay, I made it very clear in the announcement. Still, there are emails asking, can we submit multiple Slurm or this is this? I mean, come on, it's read the just read the announcement. Okay, the answer is right there. So it's I feel like now it reached a point that is seems like information I gave in the class or posted on the class website didn't get through to people's mind. Okay, so that's to me is a problem. So again, if you have friends, you know your friends, or some they miss the class, remind them. Okay, remind them to check in the website and watch the class video. Otherwise, it's become very efficient. Another thing I want to mention about the project number one is they are students who using the multi-processing algorithm, like in the from Python to for the project number one. So I want to make it clear that multi-processing library is not suitable for the MapReduce. Okay, so you may be able to, because the project number one is small. So because first of all, the multi-processing, the package in Python is for the multi-threading. Okay, it's not a parallel. We're talking about in the class. It's not parallelizing between among different computer nodes. Okay, so therefore, if you're using multi-processing, that is still you are doing the parallelization in one computing node. Okay, is within one computer node. If you're parallelizing within one computer, the problem is you cannot scale up. Say if your computer has 16 cores, then the 16 parallel jobs is the maximum parallelizing job you can do, right? So if you want to, if I say I want to using 100 the job or the 100 mappers, that multi-processing, the package cannot handle that. Okay, that means it cannot scale up. So what I'm looking for the project number one, again, like I said, the goal is not to just to solve the problem. Okay, the goal is to make you familiar with the MapReduce procedure. Okay, to scale up. Really, your program, if you simply just changing your job right now, my requirement is up to 4 processors, right? For 4 jobs. But if you're saying if you're up to 100, your program should just run just fine. Okay, so that means you need to your program is able to scale up. Okay, that's this is very important. Otherwise, you lose the point for the MapReduce. The project number one, the job itself is not that important. So if you're using multi-processing, the library from Python, you are not going to receive full credit. Okay, so that's I'll say there, because I know some students are using that. Okay, and then this is I want to say that from. So you still have time to correct it if you want to. If you just want to stick with multi-processing, that's fine, but you are not going to receive the full credit. So the correct way to do it, it should be you should use a Slurm job. You're using a Slurm, okay, to submit your jobs, and then to the CWolf, and the CWolf can do the parallelization by assigning a different computer node to do the job. So that's the correct way to do it. I'm allowing multiple Slurm submissions, so therefore you can prepare for the as I explained in the previous classes, because since you haven't learned MPI4Py yet, so I realize one Slurm file is probably not enough. So you can do 2 or 3 Slurm files submission, which that's perfect fine. Okay. If you since I didn't cover MPI4Py, that package in class, which are probably going to be in about 2 weeks, and we're going to cover that package. Okay. So I did not expect any of you to use that MPI4Py, but for somehow, if you already learned that MPI4Py, or you know how to use it, and you use in project one, that's fine. Okay, I'm perfectly fine with that. So that means you know the tool, you can use it. But if you don't know, you are not put in any disadvantage, because there are ways to solve the project one without even using MPI4Py. Okay, so that's like a few things about the project number one. I want to make it clear to the class, where you guys know what are my expectations. All right. So any questions regarding project number one, or any concerns or any problem? At this point, I expect everyone should have passed the login. Okay, Stony Brook login, the login to CWolf, that issue. If you still have issue, you should contact the CWolf supporting team as soon as possible. Okay, because now you only have a copy. If you cannot log into CWolf, that means that means you probably haven't, you are not really good at the HPC or the cluster, okay, the high performance cluster. So therefore, you're gonna facing I think you're gonna facing a difficult situation, because you learn how to use the HPC. That's also takes some time. Okay. All right. So any question or any concerns for the project number one from the yeah.
We discussed that when there are multiple jobs, we need end-to-end communicate. So what is this multi-processing?
The multi-process, if you are saying if we don't use MPI for Pi, what's the multi-processing? Yeah, so the basic right now we are not even talking about any communication. Right now we are just talking about parallelization. So the goal is for the project number one is your mapper you all have 4 parallel jobs, right? So that's just basically the very simple parallelization. There's even your so-called master node is basically is your slum your job. That's like a master node. So the parallelization will be you're gonna have a parallelization at the mapper step, right? So then you will have a parallelization job on the reducer step. So that's like a 2 simple parallelization. MPI, the multiprocessing thing, that protocol we haven't covered it. So I don't expect anyone to use it. But if you know how to use it, then you can. It's a choice that using MPI for Pi or not is a choice of your own. But again, if you don't use it, it doesn't put you into any disadvantage because there are ways to do that. So that just means if you don't using the MPI or Pi the package, then you need to having one Slurm file to submit the parallel job for the mapping step, one Slurm file to submit the job for the reducer step. You probably need a third one, a very simple one, to summarize the collecting the information, like to merge the output from the reducer to like getting your output. So potentially you may need 3 Slurm files for the whole job. Okay. Yeah, this is yeah.
Processing library from nodes.
It's talking between nodes. Like I said, yeah, you can, but like I said, I haven't covered that yet, so I don't want to discuss that too much because that's going to be for later time. This project now, you are not supposed to use it. Okay, so but if you know how to use it, feel free to use it. But I don't want to talk too much about that because that's like we're talking ahead of time. All right, any other questions? Like from people on the Zoom, do you guys have any questions? Just feel free to speak up. Okay. All right. So then this is I think that's enough about the project number one. It's it really make me nervous about the guys' first project because I expecting all kinds of issue because this is the first time, but so far hopefully okay, everybody should have got started, and I know some of you already finished it. Okay, that which is good. If you still haven't started yet, I strongly to suggest you to get started. Don't wait till your last day because the last day, if anything happen, nobody can help you. Okay. Silv support only work during weekdays. If you have anything on the weekend, if you email them, they are not going to be able to respond to you right away. Okay. Even during the weekdays, you should expect like at least like 1 day delay. So if you have a last minute question, then you're gonna kind of lose the chance being helped. So do that as early as possible. All right, so today we're gonna start to talk a little bit about like introduce a few more MapReduce algorithms, which is hopefully this can give you guys some flavor about how to use MapReducer in like a practical in real world problem. The ones we introduced before is kind of like a baby or toy examples, or baby problem, which is kind of trivial to solve. Now in here, we are kind of to go into some the problem which is more realistic. Again, we like I mentioned is so we're gonna mainly talk about this four things. The first one is about this is so-called TF IDF algorithm. This is mainly for documentation processor or documentation classification. Then we're gonna see how the MapReduce can be used in the relational algebra operations. That's like a for the if you're familiar with database, that's like the regular like database operation to pick up the column, pick up the rows, like merge two tables, and the summarize aggregation, and so on. Then after you introduce this is a relation algebra operation, then we're going to talk about the matrix multiplication, particularly within the large sparse matrix. This is basically matrix. In this case, matrix can be expressed in a way is just like a table in the database. Okay, so then this is the matrix multiplication sort of form the foundation of many algorithms, right? So if you know how to do the matrix multiplication efficiently, you can actually solve a bunch of problems. A lot of problems can eventually be reformed as the problem matrix multiplication. Then after that, we're going to learn then the problem of PageRank, which essentially is a series or sequence of matrix multiplication. Okay, so that's this is also like the roadmap. We probably need about like 3 classes to cover all the algorithm like in details. Then after that, I will spend probably 2 classes to talk about MPI for Pi. That process. After I introduce MPI for Pi, then we're gonna start your second project. Okay, second project is gonna be using to implement the PageRank algorithm. This is using this is an algorithm we learned there, but then we're gonna use MPI for Pi to control everything. So in that case, you only need to do like one string file. You will be able to handle everything within the program. Okay, you don't need to go out like right now. We're kind of jumping in and out the parallelization. So that's kind of like a roadmap. This will give you also the idea. Roughly, your second project will be like 2 weeks from today. Okay, your second project roughly is going to be 2 weeks from today, and the project I can even tell you a little bit ahead of time. So if you want to get a bit head start, that's it's using the MPI for Pi combined with MapReduce to implement PageRank algorithm. That's your second project. Okay, so let's get started let's start with the first one, the TF IDF algorithm. So TF IDF algorithm stands for the term frequency, the inverse document frequency. There's a question. Or do we really require 2 string files, one for mapper, one for reduce? Can we write into one without using the MPI? Okay, so you can try. Okay, so if you believe you don't need to, maybe there may be some ways to you can wrap everything into one string file. With multiple string file is sort of like the easiest way I can think, because then if you want to use multiple string file, you have to do some manipulation within the batch file, which again that part I didn't cover in the class as well. So If you want to wrap everything into one Slurm file, if you know how to do it, feel free to try it. But again, your code will be verified by TA. So make sure it can run. Okay, make sure everything is can work on the CWU. So I'm trying to get into this zone. How do you making this to be full screen? Where is the so the TF-IDF that's serving is like in many applications of data mining, right? So we're gonna have facing the problem, we're gonna categorize documents by their topic. So they are, for example, like in the library, right? So you have a book comes in, then you want to classify the book to some categories by this content. So that's like a digital library. Okay, in the future, that's probably there's a human category. Used to be this job done by humans, but in the future it was like the books was kind of generating at a speed which is kind of like crazy, right? So now the particularly within the ChatGPT or the large language model, you can write in books like within days. So by classifying the documents by human is kind of like become very slow. So we need some algorithm to categorize the documents. Another application would be for the Google. The Google they call so like are getting a lot of this web. They crawl they script like a lot of web pages from the internet, and then they want to classify these web pages into different categories to increase in their search efficiency, right? So if it's come from like music, from sports, or from like the politics, so they want to attach some tag to them. So making this is a classification problem. But this classification problem again is you cannot do it by human because there's just too many of them. There are so many websites or so many the documents out there. This in terms of the scale is at the billions, okay, at the billions level. So how should they do that? So that's a problem. So for the documents to human, if we read it, we can understand it, we know its meaning, we kind of can grasp, can extract it, like what kind of the information you talk about. But to an algorithm, it's just a sequence of words, right? It's just then that's so we have to somehow to get information from sequence of words to make the classification. Now the classification often start by looking at the documents and finding significant words in documents. It's so the words in the document define what the document is, and then we can assign the classification. Now, just intuitively, you can see the words that appear most frequently in a document should be very important to classify, right? But there's a problem because usually the words appearing with most frequently in a document are actually not useful because those words are this is sort of like the common words, right? Like the and this is sort of like those words that appear most frequently in the document. They're actually not very useful for classification. Okay. Now the indicator for the topics are typically the rare words, right? Such as like a chucker for polo, right? So you know if you know the football, you know it's a sports. But some words are also pretty ambiguous, right? Like apple. If you see, you could be tag, it could be fruits, right? So then it also depending on other things. Now there's another twist is not all the rare words are equally useful as indicator, right? For example, the word notwithstanding or albeit. This word is kind of like people don't use it that often, but it's still this word is just like it's Windows. It's kind of like they are rare words, but they are not meaningful to classify. So the TF-IDF is kind of like a formal measure of how concentrated into relative few documents are the occurrence of a given word. That's to be used into for the classification. Now let's just think about it, right? So if you want to design algorithm which is try to measure, find the keywords that can be most useful for the documents classification. So what do you think? Like what are the most important characteristics? Like if you this is like I'm posted out as a I mean next slide I'm gonna talk about it, right? But just if without looking at the slides, if you just intuitively, if you have this problem, you have like a 1 billion documents. Just think about as why you're going to design algorithm. So what are the should be the goal is to find some words, right, which can be used to classify the documents. So what should be the characteristic for the words which have in this classification ability? So what kind of words we should looking for? Like any idea? Just think about it. So there are two things, right? So one is the word frequency in a document. So like, do you think is the more frequent the word appear in a document is useful for the classification, or the words like appear less frequency or infrequently in the document is more useful for the classification? Depending on the just in general. Less frequent. Okay. So but if you like in a document, if that word only mentioned once, do you think it can represent that document? If it's less frequent, right? So if a word has been mentioned like 1,000 times in the document, do you think like the word mentioned once or word mentioned 1,000 times, which one you think is more meaningful for the classification? Right. So you want to be if the word frequent document, you think so like you have more frequent, it should be better classification, right? But there's a twist, like we mentioned here, but not all the frequent. If for the and the n, if you appear frequently in a document, they are actually not useful. So what should be? How can we get rid of this? How can we sort of like get around this? Is the first constraint. Like what do you think is what kind of the condition we can add on to making this is like words appear most frequent, to basically filter out not all of them, but filter out a lot of this is common words.
Let's say there are 1,000 words.
Yeah.
But generally, when a writer writes an article, he'll not use 1,000 words for the same one. So somewhere around the average, like if every word is around, I mean, averaging out is 500. So somewhere around that range would be the title of the article.
Yeah. So you are trying to say is so if you're author using like 1,000 words to write the article, and then you try to say some of them gonna use it more frequent than others, yeah, to classify them. Yeah.
It's like sample 2,000 documents to get a range sample of documents to get a word frequency, and you see things that like run and here that's something right, and you can now rough scaling where you can scale and
Yeah.
or sharing the documents.
Yeah, that's also not bad. But I think the real solution could be actually simpler than that, because think about this is the and this is this kind of word. Are they gonna appear in just like some documents, or are gonna appear in all documents? Yeah, we can remove them. The another thing is we can calculate find out how popular these words among the documents, right? So if you like, if the word appear in all documents, basically we can remove them. They are actually not very informative because it's everywhere, right? But if this word is only appear in a small segment of the documents, say you have like 1 million documents, but if there's one word that's only appear in 1,000 of them, is that kind of like more informative, or is that useful, right? So the second one is the frequency. This is like word frequency in a document. The second one is kind of word, is not the frequency. It's actually, I should see the word, what should be probably, I can use the word frequency in all documents. So this is to be basically saying is if the word is less spread in the documents, it probably has more informative for the classification, right? So basically, if we put in these two things together, okay, the best word that can be used for classification would be the one who appear high frequently in some documents, but not all documents. Would you agree? If you have 1,000, if you have 1 million documents, but suppose there's one word, there's a word like football, it only appears, say, in 1,000 documents, but among these 1,000 documents, the football, the frequency being mentioned is very high, right? So then you kind of like say that 1,000 documents kind of like I can use in football to as a tag for that documents, right? So that would be the idea behind this TF-IDF. So you want to find these words which are concentrated in a certain small percentage of documents. But when they come up, when they mention in this small percentage of documents, they can be mentioned like at a high frequency. Okay, so that's kind of like if you have that intuition behind it, then we can build up this so-called TF-IDF. So TF-IDF basically is a capture, is like using mathematical formula to measure this is intuition. Okay, so measure intuition. The question is, how do we do that? Okay, how do you do that? So yeah. Blind. It doesn't consider any domain knowledge, right? So you want to find some word which can represent some kind of, hopefully is like a domain knowledge, right? This is football, you can't represent it, this is a document. So that's in here we don't have any prior information, okay? All you got it is just a bunch of sequence of word, which is each sequence of word is a document. That's all, right? So the algorithm actually, if you understand that this is the kind of intuition, the algorithm actually be pretty then become pretty easy to understand. So the TF-IDM algorithm, IDM more like a measurement. Okay, it's a measurement. It contains two items. Okay, one is the TF item, one is the IDF item. So let's just make a notation straight. So suppose we have a collection of n documents. This n can be large, okay? Say like 1 billion, okay? 1 billion documents. Now, if we define Fij to be the frequency or the number of occurrence of the word I in document J, okay? So I is stand for each word. J is for the document, the number. Now, suppose term I appear in Ni of n documents. So out of this is n capital N documents, like 1 billion documents, there are Ni's, the small Ni, okay? There are Ni of them contains term I. So this is measured, basically is how concentrated this word in like is in the documents, right? So then based on this notation, we can define the TFIJ. This will be the term frequency of word I appear in the document J, will be equal to Fij defined by maximum of Fkj, okay, over K. K is over all the words. So this is basically TFIJ measure the frequency of term I in document J. The denominator here is just to rescale it up, right? Rescale it. So if you have like a maximum, if your maximum frequency is 1000, then if another word appear 500 times, you just say rescale to 0.5, right? So we just making this to be comparable among the from documents to documents. Otherwise, if you don't normalize it, if you're just using the raw frequency, then there's a word maybe mentioned 10 times, or like word may mention like 100 times versus another word, same word mentioned in another document like a 10,000 times, right? So then maybe not the fair comparison, because for the first scenario, the documents may be short, okay, maybe only contain like 1,000 words. Then if you mention 100 times, actually it's pretty frequent, right? It's very frequent. But in the second document, is 10,000, but the word may be like 10 million, right? So in this is the denominator basically try to normalize it to that scale. Then also making the term frequency to be in the range of like 0 to 1, right? So that's but the key idea, the term frequency, is try to measure how frequent of the term I or the word I appear in a document J, right? So this is the first one. This is measure how frequent of the word in a document. The IDF inverse document frequency is captured. The second idea, okay, is say how concentrated this word how concentrated the word in among all the documents, okay, among all the documents. Notice here the IDF, it only has a subscript I, okay. It means it only is a feature for the term. So the so-called inverse document frequency, because if you measure the frequency of the word out of this capital N documents, what you really should do is just do Ni divided by capital N, right? So this is the frequency, right? This is the frequency of the word I appear in all documents. Now, but as we understand, the smaller this value is, the more valuable for the words, right? For the classification. So therefore, we actually, instead of doing this is percentage, we reverse it, okay? Reverse it to making this is this is why it's called the inverse frequency, because then that means the larger number IDF, the more valuable is for classification. And we put in the log 2 scale again, is just to try to making this two thing they're scalable, because otherwise if you don't do it, then if there's a word appear like in one document, if you have 1 billion, then this number become huge, right? So log 2 scale, just try to scale it down. Now, then finally, the TF-IDF is basically just TF-IJ multiplied by IDFI. So that's this is how it's defined. Now, the algorithm, the measurement is it's pretty, after understanding, okay, after I explain, it's become pretty straightforward, right? But I think the beauty about this algorithm is, although it's very simple, but it's very useful, right? It's very useful, and it's very intuitive. Another reason I want to mention this algorithm would be sometimes in real life, okay, particularly when you do the data analysis, you have intuition, right? You have intuition, and then to formulate that intuition into a mathematical form, that's actually is a pretty important step. Okay, pretty important step. I hope is another thing I want to say is that's why I want to, before I go into the formula, I want you guys to have an intuition first. Okay, then you try to see from this intuition how can we formalize them. This is into a matrix or into a number, and then this number can be used for the classification or for the algorithm. Because if you cannot formulate them into particularly for these documents or the words or the language, if you cannot formulate them, then it would be hard for us to do any the further computation, right? Even for the large language model, then still people still have to you have to vectorize this is a word into putting the vector space, and then you can do the operation. So this is another example. I think this is a simple but beauty to show you how to convert this intuition to the algorithm. There's another algorithm which we're gonna cover later on as well, is support vector machine, which is we're gonna cover that in I'm gonna explain from in how you have intuition of developing the algorithm. That's also very beautiful algorithm. Yes.
Are we assuming that the documents do not contain any title?
You mean the here does not contain any title?
Are we assuming that? I guess instead of scanning every document, you can scan the title of the document. That is good and fine.
That's another thing, right? So for now is basically I'm just saying in titles, title is sometimes the title could be misleading. May not have enough information into there. The title is a good start, but eventually if you want to understand it, then this still has to be go to the full documents. So you can apply this TF-IDF on titles as well, right? So that's perfectly fine. Yeah.
Six papers will like coin a new term and then immediately reference that term in the rest of the paper as an acronym. Meaning that like that term only appears in the document very, very frequently.
Yeah.
But the acronym is referenced constantly.
Yeah.
How does this deal with that?
So okay, so let me just say the more frequent will help. Oh, that's the big. So this is gonna be if you in here, right? If you here, what you're gonna see is that word itself is gonna appear. See, this n is 1, right? So this is gonna be a huge number, and you're gonna have in the frequency of here. So you're gonna have your high term over here. Okay. Now this is just the input. So the TF-IDF, what you should think is this is your word, all right, this is your documents. Eventually, what you're gonna form is let's say the NW, ND, right? What you're gonna form is this is a big matrix, right? It's a big matrix. So then the TF-IDF, what you're gonna say is you're gonna fill up the number in there. So what you want to do is using this as a matrix, because then once you form this matrix, then it's become an unsupervised problem, right? It's become an unsupervised problem. So you can find, hopefully what you're going to find out is you're going to formalize them into some this kind of blocks, right? Into this kind of blocks to making this is a making this is so-called classification. Now, if you have in the case like I mentioned, if you have one the documents, which is like one word appear very high frequency in some documents, and also then this ideal value is very, very high. Now that document itself, basically it can be formed its own category, but at the same time, because it also has other words, okay? So then these documents, depending on how how you gonna like what's the granularity of your classification you want to be, right? So if you want to see, really want to go down to like at a very very small details, then this itself may become one cluster, right? But if you see I want to do this is not that fine classification, but I want to do it more like a course level, like I want to have 10 categories, right? At the beginning, I want to have 10 categories. Then very likely this one, although this one number is very high, but it also contains many other words, okay? So many other words, hopefully you're going to have information can also overwhelm this one particular number, and you will be dragged into some like a big classifier, okay? So that's likely what can happen. So the what you can also I mean this would be the like more like a subsequent or the consider downstairs how to do the analysis, because you can put in some filters into there, okay? Filters in there. As a matter of fact, the people often do that. You see, if you for those like the and you know those words which has no information, you can basically get rid of them from your matrix. Okay, so that's mean you can cross out. Say this word is n. You basically just cross it out, and then you can do the classification. Or you can see if there's only one word is only appear in one document, I don't consider that word, right? So it's so that's you can specify some like a minimal threshold. Say the word has to be appear in some small percentage, right? Very small, like you have to appear in like a 0.101% of documents in order to be meaningful to be classification, right? So there are some things you can tweak, okay? But this is I think to form them into this numerical value. This is just the first step. This is not the full algorithm for like the full classification, but it's you have to start from somewhere. So that's something is provide the so like the input for the algorithm. Okay, you can fine tune with a lot of the details. Okay, so that's this is the algorithm. Now then let's see how can we implement it in the MapReduce fashion. Again, it's a good example. It's a simple algorithm, right? It's a simple algorithm, but I in my view is a beautiful algorithm because it tells you because the thing is to identify these two terms building from intuition, and then you have to somehow figure a way to normalize the term frequency, and then even doing putting the log 2 on top of it. These are like details. Okay, these are details. If you're given this is you see that's very important. It's very easy to understand. But if you're not given this one, if you just starting this is a problem, and you to develop this, you can think even to get to this step is actually not that straightforward because you have many options. Okay, this seems to be in this particular form seems to work well in the real problem. So yeah, I just want to point out so when you go back, you really close your eyes to think about this problem and then see if you can come up something different. Okay, maybe you can even come up something like smarter than this. That's maybe there are other ways to do it. Okay, but by looking at this is I think that's if you just stop at it and just understand the term, then that's just to me it's kind of waste. You should thinking through the logic. You're gonna feel I think it's gonna benefit you more. So to implement it, then using apparently since we're talking MapReduce, right? So next thing we're gonna say is how do we using the MapReduce algorithm to implement this is a TF IDF the matrix. So information basically we need this information, right? So we need the number of times of term I appear. If you look at the formula, right? We need Fij, right? So we need to figure out what this Fij. We need this is the numerator. We need the denominator, the maximum of this Fkj, right? We need that. We also need n. We need ni. So we basically need 4 numbers, right? We need these 4 numbers. Now the number of terms this is the number of times term I appear in a given document. This is Nij, right? This is Nij. Number of terms in each document, right? That's sort of like the denominator. Number of documents in which term I appear. This is a small ni. Total number of documents, that's capital N, right? So that's basically these are 4 numbers. We need to calculate these 4 numbers in order to calculate this TF idea. Now, the job number 1 is we're gonna find out the word frequency in the documents. So I want to highlight this so you guys can see. Now, for the mapper you're gonna have in the input for the mapper is basically you can use in the document name and the content as a key value pairs, right? So then this is a document name. This is a document J, right? This is a document J you having. Now document name, this is like the title or the of documents, right? So or it just could be just simple numbers, okay? So you give into to the documents. So the input is if you have say 1 billion of documents, right? So you're gonna have this is the input. Now the output could be the word, okay? Because next thing you want to do is you want to calculate in, remember your goal is your Fij, right? This is the goal is try to figure out the word frequency in your document. So then your output mapper is gonna be the word and documents, right? Word and documents. So each word it appeared, then you attach the doc name to it, and then you have it appear once, right? You have 1 into there. Now the reducer basically you want to sum up the counts for word in the documents, right? You having, remember for the reducer, what you're gonna do is gonna collecting all the key value pair with the same key, and then you just put in putting all the values into a big list, right? So in this case, it's because you're gonna have a list of ones. So therefore, the reducer job is sum of the counts for the word in documents, and output is gonna be like this. You want to have in this is the word I appear in document J and within a frequency F, right? So that's the F is the frequency. Now, I don't know if you having noticed this. The output of your the output of this whole MapReduce job determines what key values you want what is the key value, what basically is the key, what should be the key from the mapper output. Okay, so see, for example, your job, the job for this MapReduce job, you want to find out the frequency of Fij. Okay, frequency Fij. So you want to find the term I in document J. Then the key for the mapper output should be the Ij, should be the word and documents, right? Because that's will be the key, because this frequency is applied to here. So in another word, is a subscript of your output, overall output. It should be serving as the key of the mapper output. I don't know if you get that point, because you want to map it, because what the reducer do is just to summarize information for that particular key, right? For particular key. So your key, if your whole output is on each word on each document, then the key for the mapper should be also on each word on each document. Okay, so this is if you understand that, then you remember I told you for the MapReduce job, one of the important thing is try to smartly to using the key value to design a key value. Okay, so this is one of the things. So in this cases, you would understand why in the mapper you have in this input, why the output you need to do the key would be a word and document together. That's your key, because that's when you at the end of the job you want to find a frequency for each word and each documents. So they have to be the key for the map output, right? So they have to be a key for the map output. That's this is the logic. All right, so then after this step, okay, after this step, you will have what you have is Fij, right? So this is this is the frequency, this is your I, the word and document. So basically, you have Fij being calculated. Now the second job you want to do is you want to do the word count for each document. Basically, you want to find out the maximum for the documents. So the outcome you want to find out is for each document. Remember, this is now the second information. Okay, the second one in the job number 2. What do you want to find? What do you want to find is you want to find maximum of K of Fkj. Okay, this is for the second job. This is what you want to find. Now in this guy here, this is the quantity. Okay, this is the quantity. Basically, is some kind of not really the F, but we can say call it some value of X, right? So Xj. So this is the quantity is related to each documents, right? So each subscript should be documents because your maximum over K, the K is gone, right? The word is gone for that documents. The word is gone. So therefore, since this is your final output from this mapper job, so the key for the mapper output should be J, right? J. What is J? J is an index for document name, right? It's document name. So therefore, that's why the mapper output, your key should be document. Okay, your key be document. So therefore, the input you're gonna have in the Fij. This is your Fij as an input. Now your output for the mapper, well, you have in document as a key. You have the word and the frequency for that document. You attach to them, right? You attach to it, and you have in this is you still want to keep the information. Now for the reducer, what are you gonna do? Now each key is the documents. So then this reducer is gonna, for each document, you're gonna have in all its word and the corresponding frequency attached to that document name, right? So then the reducer we're gonna do is find a maximum frequency of all the F's in the same documents, right? So remember, so now the reducer input, okay? The input of the reducer is gonna be doc name. This is the key from mapper output. Then this is gonna be the key. Then you're gonna have the list, right? You're gonna have list. You're gonna have in the word 1, frequency 1. This will be the first value attached to. You have the word 2, F1, and so on. So you're gonna have a bunch of this is a list, each within this word and its corresponding frequency attached to that document, right? So the words will be all the words appear in the documents, and their corresponding frequency in the documents is also being collected. So this is the input for the reducer. And then the input reducer is just try to find a maximum of the frequency among all the words that appear in that documents, right? So in here, this is then find, once you find this is a step. So what you have here, for here after this step, okay, this is basically you have in the MF, maximum frequency, basically is equal to maximum of the over K of this Fkj, right? So this is we denote as FMF. Now for the reducer output, you have to consider the next step, right? So then the reducer output is you're gonna put in the word and document as a key, because eventually the TF IDF, what you want to do is still on each word and each document, right? So therefore you want to have in this is a word document as your key, but now the value is you're gonna have in for each F and MF. This then for each word and this document, you're gonna have its frequency and also has the maximum frequency for the document, right? So that's up to here. You finish the TF calculation, okay, the term frequency calculation. So what do you need to, what are you doing here is just essentially the job is very simple. You just you just try like to manipulate this, what it should be the key, what should be the value, and then the reducer is, what the reducer doing is actually just simple, simple calculations. Okay, is this clear? Or is any question on this? Okay, great. Now, so once you finish, this is the Fij, and also maximum of the key of Fkj, right? So that's a TF part, term frequency part is done. So then the second next one, we need to figure out the Nj, Ni, and capital N, right? Ni is a number of the documents where term I appeared in. This N capital N is the total documents. So that's relatively easy. So so notice here the job 1, job 2, job 3, they are all concatenated. Okay, where I'm doing the chain, I'm chaining all the different map reduce. That's also give you the idea. For the mapper and reducer, its output should be the key value pairs. Its input is key value pairs, output is key value pairs. So then we can chaining them, right? So this is an example of chaining them. So in the third job, your input will be the Word document, FMF. So then you want to calculate for the Word, how many. So the third job, you want to find out the Ni. Okay, you want to find the Ni. Ni is what? Is to each word, right? I is for the word. So therefore, the key of mapper output should be word, because you want to find this is for the word, right? So then the key for the mapper output should be word. So that's why in the input will be word documents FMF, but then the output should be word document name, right? F the frequency is a corresponding maximum frequency in the document name, and 1 to attach to that. Okay, to do that. Now the reducer basically just sum up the counts for the word in this columns, right? So if the word appear in the document, you can have in one record, right? You have one record. So therefore, then you can just basically from the reducer, what you're going to do is just calculate the Ni, and output. Again, you want to, because TF IDF is on each word and its document, so you're back to the word documents as a key. And then now you put in another value like a Ni into the value attached to that. So you have in F, MF, Ni, right? So you have these values. Now job number 4 is assume you assume that capital N is known, right? Capital N is known. If capital N is not known, you can just basically just do another job to count how many documents have, right? So that's really simple. So then once you have in this, then the documents you input is the Word documents. You have F, MF, Ni. N is known because N is quantity does not depending on the Word documents, right? So if it doesn't know, you can just using a map reduce to find it. So the output you just do this, right? You have in each word each documents, then is TF it just be F over MF times log Q kept N over Ni. So that's and the reducer could be just identity function, because you don't need to do anything else. The calculation has been done in the mapper. So you can see by the job 1, job 2, job 3, job 4, you're chaining all the 4 jobs together, and then at the end you can have in this is a TF IDF number being calculated. Now I think this is example is a good example, because it can illustrate actually several concepts into the what we learned from the previous class. The first, like you chaining, how to chaining the jobs, right? How to determine the key value pairs, and also it actually solving a problem, right? So the goal is for each MapReduce job itself is not that hard. It's actually pretty simple. But by breaking them down one by one, now you can have pretty good useful information. Now, this is the algorithm is pretty is pretty simple. But if you want to work if you work at a scale, then we still have to we still have to do some so like the small tweaks, right? So we'll have to twist the algorithm a little bit. For example, right, coupling this documents frequency and maximum frequency counts, right? While summing 1 into ni may not fit into memory, right? Because in this case you can see when you try to summarize this image, just think about how many documents contains the word the, right? Word the how many documents. See, if you have 1 billion documents, then it's very likely the is going to appear in every document. So that means you have like 1 billion record. So that's you may not even fit in everything into memory, right? So I mean it's possible you can fit in, but it's so possible you couldn't fit in the memory. So in that case, how are you going to do that? I mean, a possible solution would be you can ignore those very high frequency word. If the word is appear like in is going to appear in almost like every document, then you can basically cross them out, right? Or you can write out the intermediate data into a file using another MapReduce pass to handle this. So when you go up to scale, okay, that's what I'm in the project number 1. That's why I emphasize scalability. That's why I'm saying the multiprocessing that thing multiprocessing package from Python you cannot use in the project 1 because it cannot scale up. Okay, because when you scale up, that's typically the problem may occur, because even you run like a toy examples, with small data, you can run perfect fine. But once you get into this is the big scale, even for the like the summing ones, it's a simple operation may not be may fail because then you just simply have too many of them. It can crash your like a single node. Okay, the comment seems like. For some other thoughts on the TF-IDF, that's it's about several small jobs add up to the full algorithm. This is true not just for big data, it's actually true for a lot of things, right? So like a mathematical proof is the same thing. You having a sequence of the small steps adding up, then eventually you can end up with a very sophisticated theorem. This is so don't underestimate the power of small jobs. That's if you have the ability to break in the big task into smaller tasks and then finish each of them, that's a very good skill. They're having lots of code can be reused, right? The stack, the store class exists for aggregation identity and so on. Job 3 and job 4 can really be done at once in same reducer, saving a right read circle. Because I'm in here the example job 3, separate job 3 and job 4 is just for, I mean, it's basically just making it clear, right? You want to for each pass we have each calculation. But this is for the job 4. It actually can be merged to the, because all the information here is already being here, right? It's already job 3. So we can essentially merge this job 4 to the job 3, which is fine. Because for each MapReduce recycle is involving read and write to the hard disk. Okay, slow down. So if you can like save one cycle, that'll be worthwhile. Then this algorithm can very easy to handle medium large scale, but must take care to ensure the flat memory usage for the large scale, right? So that's what we covered. So the question is, can we just add them in mapper for counting instead of saving P1 shape? I'm not exactly sure which step you're asking for. So there's a question on Zoom. So you are Okay, so if you have because I did not monitor, this is a I don't know what type you ask, but if you having if you have like you still have problem, like I said, for the map reuse, there are many of steps. What I'm doing here is may not be the optimal way to do the run map reuse. The way I'm showing here is just try to see which task I'm just trying to give you output, right? This is like this is Fij, this is the maximum of Fij. This is like a NI. So the way I implement here is not the optimal way, but it's to my view, but it's probably the most clear way to present it. Okay, so but if you want to, I'm sure there are spaces to like just like combine job 3 and job 4 together. You can make it better, but this is just taking this as an example. Don't view this as like the most optimal way to do it. Okay. Okay, so then this is the TF IDF. Now then the next topic I want to get started, okay, because I still have about 5 minutes left, so I want to get started. So then we can talk about details in the next class. So next the group I want to mention is relational algebra operations. For the operation using database queries, MapReduce can be very useful. As a matter of fact, a lot of MapReduce is actually just it can be viewed as your operation on large database, on huge database. Okay, that's essentially the MapReduce is about. So working within the database it's kind of like the one of the job like MapReduce do. Now I don't know how many of you have database background, but I just want to introduce some very simple terms just to make sure everybody has on the same page. Now, a relation, okay, in here, a relation is basically a table with column headers called attributes, right? So relation, you can think about it just a table, then with each column called attribute. It's just very much just like a data frame, right? It's very much like data frame. But in this case, we call it a relation or a table. Okay, it's just a table. It is a table, but just within the column head. Each table, each column has a column head, and then column head we call attributes. The rows of the relation we call tuples. Right, each row, like in here, the below is the relation. We call it a tuple, and then the set of attributes of relation we call it a schema. Right, so like in here, the from and Q, that's a schema for this relation. So we often write the expression like a R A1 A2 up to AN to say this R A1 to AN, this is representing a relation within the name R, and its attributes are going to be A1 A2 up to AN, right? So A1 up to AN, this is it's a schema as well. So this is below here. This is an example of a very simple relation with two attributes, right? Two attributes. One is from, one is to. That's from the URL. This is how the PageRank, the input for the PageRank is you having a URL, which is we're gonna have from, and this URL is gonna point to some other links, right? Another URL. So like say you are from this website, URL 1, you're gonna point to 2 and point to 3. And 2 is also point to 3, 2 can point to 4. So basically, you're going to have this is a sort of like a big graph, and then the goal of PageRank is try to from this big graph and to rank to find out which link which URL is like more important than others, and then give them a numerical score, right? To evaluate them. So the standard operations on the relation we call it a relational algebra is pretty much this is like a five operations. The simple ones, one is a selection. Selection, that's essentially just to apply a condition to each tuple in the relation and then produce output only those tuples satisfy the condition, it will be output, right? So you have this the from and to. So you say I only want to pick up those are the ones with the from URL1, okay? From is equal to URL1. So you apply a condition, and then this condition will be applied to each row to see if that row satisfy the condition or not. If you satisfy condition, you keep it. If you don't, then you just remove it, right? To generate a new relation to there. Now there's only one. So it looks very much just like the database, the data frame, the filtering, right? Like query your filtering database, the data frame for each row. The only one thing is database does not allow duplicates. Okay, does not allow duplicates. So if you have two rows are the same, basically you're going to remove one because that's duplicate information. So that means each row in this relation, each row is information has to be unique, right? Each row information has to be unique. Now, the selection problem would be once you have to do the selection on the rows, once you remove some of the rows, then the rows could become duplicate. Okay, could become duplicate. So in that cases, we kind of have for this one is not. We is more like projection. So selection is selecting rows. Then after you do the operation, if there are two rows become the same, then we need to sort of like remove a duplicate. That's the only thing when we do the so-called relation algebra. That's what we need to do. Projection is for some subset S of the attributes of relation we produce for each tuple only the components of the attributes in S. So this is for the projection. Basically, you just selecting the columns, right? You say from this is a relation. I only keep the from the column. So then you keep the from, and then by the remove duplicate, then that's give you the projection. And there are union, intersection, difference, natural join, and the grouping aggregation. Okay, so those are things we can talk about in next class. Okay, all right, that's all for today. We're gonna see you on Wednesday.